What happens to the chain of evidence when an AI model commits multi-million-dollar fraud autonomously, and the only proof is an ephemeral API log designed to delete itself within hours? Welcome to reWant, Courseware, an AI-narrated video series unpacking the latest lectures of Professor Adam Scott Wandt of the John Jay College of Criminal Justice in New York City. This video examines how the migration of AI processing to the cloud and the network edge has changed traditional forensic timelines, requiring a different approach to digital investigations. Digital forensics and incident response, or DFIR, is the discipline of identifying, preserving, and analyzing digital evidence. Professionals in this field are now adapting their methodologies to investigate these decentralized and highly volatile AI-enabled frauds. Traditional forensic methodology was built on persistence. Investigators relied on securing physical custody of hardware to acquire the exact storage sectors where an operating system wrote its logs. The modern AI ecosystem replaces single devices with three tiers: edge AI devices, cloud API gateways, and downstream application servers. Evidence is fragmented across volatile memory sectors and transient gateway logs, which, unlike physical drives, are configured to overwrite or delete themselves automatically. This creates what can be described as a forensic evaporation point. If an investigator waits for the normal pace of subpoenas and warrants to unfold, the critical cloud evidence will be gone before they begin. Prompt injection is currently the primary enterprise AI threat vector, occupying a critical rank within the OWASP Top 10 framework for large language model applications. In cases of indirect prompt injection, attackers embed malicious instructions within standard vendor documents or websites. When an enterprise AI assistant processes that content, it ingests the hidden instructions as part of its normal workflow. This risk scales with Agentic AI. These are autonomous systems designed to browse the web, execute code, and initiate financial transactions in multi-step sequences without continuous human direction. A single injected prompt can hijack the logic of an agentic AI, causing the model to operate entirely outside its intended safety parameters and execute actions that contradict its system prompt. This leads to tangible consequences in downstream systems. The hijacked AI may package and exfiltrate corporate databases to external servers or manipulate internal financial records. This creates a significant attribution problem. Because the AI model was invoked by a legitimate application, the malicious actions are logged under a valid authorized user identity. Traditional authentication logs show no evidence of stolen passwords. Investigators must instead identify the attack through the anomalous behavioral sequences the AI performed. The financial impact of AI-enabled deception is massive. In 2024, a finance employee at Arup was deceived into transferring approximately $25 million to fraudulent accounts. This was an instance of business email compromise, or BEC. In these exploits, attackers use compromised identities to deceive targets into initiating unauthorized financial transfers. The Arup case utilized a synchronized deepfake video conference. Attackers impersonated the company's chief financial officer and other executives in real time to build trust during the call. The deepfake video itself, the primary instrument used to deceive the employee, is almost never retained on video platform server logs after a live session ends. When the primary deception leaves no direct media artifact, investigators must rely on reconstructing the cross-system action trace. Reconstructing the event requires working backward from the financial transaction to find the network activity the AI left behind in secondary systems. This process begins by extracting the Cloud AI API gateway logs, which capture model invocations, token counts, and session metadata. Unless extended logging is enabled, they will not contain the text of the malicious instruction. The prompt content field is typically redacted. According to NSA and CISA guidelines, these logs carry very short retention windows. Investigators must secure immediate legal preservation holds and perform SHA 256 hashed account exports to protect the evidence from automatic deletion. Investigators then correlate API timestamps with corporate DNS query logs. This reveals whether the AI requested the domain resolution of an external command and control server. The search continues at the device layer using the master file table, or MFT. This is the ledger in Windows environments that tracks when every file was created, accessed, or modified. MFT artifacts provide ground truth corroboration of the cloud logs. They document exactly which local files the hijacked AI actually accessed during the suspected incident. A prosecutable record exists only when investigators successfully link cloud API metadata, outbound DNS queries, and local MFT records into a single chronological timeline. Forensic complexity increases at the network edge, specifically with IoT devices like smart cameras and sensors that use embedded inference chips. In edge AI architectures, the device processes raw physical sensor data locally to make immediate classifications. To manage storage, these devices are often configured to discard original video frames or sensor readings immediately after the AI processes them. This reduces the evidentiary record to the AI's generated metadata. Investigators are left with timestamps, classification labels, and confidence scores, but no raw data to verify those outputs. When raw data is missing, the investigator must verify the AI model's training provenance and validation history to determine its reliability. Examiners must also audit the internal metadata consistency. Discrepancies in confidence scores or sudden model updates can indicate that an attacker manipulated the localized model. At the network edge, the digital investigator is no longer analyzing a direct recording. They are auditing a machine's interpretation of an event. Extracting ephemeral API logs and edge inferences is only the first step. For this evidence to be used in a trial, it must satisfy the requirements for legal admissibility. In federal proceedings, AI-derived evidence is evaluated against the Mathews v. Eldridge balancing test to ensure procedural due process. This framework weighs private interests against administrative burdens, focusing on the risk of erroneous legal decisions. Relying on opaque AI and discarded data increases the risk of erroneous deprivation. These artifacts are difficult to challenge without specialized access. To satisfy constitutional standards, legal scholarship suggests implementing specific procedural safeguards. These include the mandatory disclosure of model parameters, providing experts direct access to the algorithm, and ensuring the opportunity to contest the accuracy of the AI's output. Without these safeguards, federal courts may find that the evidence does not meet the standards of procedural fairness and could reject AI-derived artifacts entirely. Technical extraction is only one component of a modern investigation. The final test for an investigator is whether the evidence meets the strict standard of constitutional review required in federal proceedings. The future of digital forensics is moving beyond the recovery of hidden files. It is now about chronologically proving behavioral intent within autonomous systems. Investigators must now work at the intersection of volatile cloud infrastructure and the specific requirements of legal due process. Like, follow, and subscribe for more deep dives into emerging technology, digital investigations, and the ideas shaping our future. And remember, stay curious and want knowledge.